So now we would like to find out about the performance of spatially coupled LDPC codes. And for this, we're looking at density evolution. Respectively, we derive density evolution, and we're looking at some thresholds of spatially coupled LDPC codes. So we can essentially track the asymptotic behavior of the spatially coupled ensemble, just as we did for LDPC codes. But we need to make sure that we have a multi-edge type ensemble, so each spatial position may behave differently. So for simplicity, we first restrict ourselves to the binary erasure channel. We can analyze general channels using the Gaussian approximation. The extension is kind of straightforward, but we'll not do it here. So what we are interested in is, again, the decoding threshold. So instead of tracking just one single erasure probability, now we need to track L different erasure probabilities, CL, CT, and we need to have a specific C for every possible spatial position. So CTL is the probability that an outgoing message from a variable node at spatial position T is erased in iteration L. KTL is the probability that the outgoing message check node is erased at spatial position T in iteration L. And now we are looking at the calculating those messages specifically. So we're looking at every variable node. We're looking at a variable node in spatial position T. And this one is connected with probability 1 over W. Sorry for this overlapping. Probability 1 over W is connected to a check node in spatial position T. With 1 over W, it's connected to a check node in spatial position T plus 1. 1 over W, it's connected to check node spatial position T plus W minus 1. So the probability that an incoming message is erased is 1 over W chi TL plus 1 over W chi T L or chi L T plus 1 plus 1 over W chi T plus W minus 1 L and so on. So it's the average probability of the W plus W possible spatial positions it's connecting to. So, and by incoming message I mean because here we're looking at the variable node specifically. We're looking at the variable node. Can have messages coming from spatial position T, spatial position T plus 1, and spatial position T plus 2, and so on. And we average the probabilities, or we take a look at the average probability that the message is erased. We have a random process that defines where it is connected. So the probability that it is erased is 1 over W times the average over chi T plus I. The average goes from 0 to W minus 1. So now we know when is the outgoing message is erased from a variable node, if the channel message is erased, and if all the incoming messages are erased. Erase if the channel is erased, which happens with probability epsilon, and if all the incoming messages are erased, so this is the probability that an incoming message is erased, to the power dv minus 1. That's it. So we have CTL is epsilon times this average to the power dv minus 1. Variable nodes done. Now we're looking at the check nodes. So we're looking at the check nodes. So again, due to the reciprocity, each check node at spatial position T is connected with probability 1 over W to a variable node at spatial position T. Connected with probability 1 over W to a variable node at spatial position T minus 1, and so on. So the probability that an incoming message is erased is again 1 over W times the probability that the incoming message from spatial position T is erased. It's 1 over W It's the probability that you go. The edge comes from t minus 1, that this message is erased, which is ct minus 1, L minus 1, and so on. Again, it's the average of 1 over w times the sum from j going from 0 to w minus 1, c t minus j at iteration L minus 1. Now we know that the outgoing message is not erased if all the incoming messages are not erased. The outgoing message is erased if it is 1 minus this probability that the outgoing message is not erased. All the incoming messages are not erased with probability 1 minus average to the power dc minus 1, and then we have another 1 minus in front of it. All right, so now we can put everything together, just as we did before, and we can say that c t epsilon is epsilon times the summation, and this is equal to chi t L to the power dv minus 1. And then we insert, we go back, we see that this is chi t plus I L. And then we insert chi t plus I L. So see here, we have the summation over chi t plus I L. We see that this is equal to chi t plus I or L. And then we insert the expression for chi, which again depends on xi. And this is 1 minus the summation xi t minus j. But now we need to insert t plus I. So it's xi of t plus I minus j to the power dc minus 1. And then this we can simplify this a little bit. The sum over 1 is equal to w, divided by w is equal to 1. 1 minus 1 over w, sum from I going from 0 to w minus 1, times 1 minus 1 over w, sum going from j equals 0 to w minus 1 of c t plus I minus j, then power dc minus 1, power dv minus 1, as we are used to it. So this is the final expression for the density evolution for spatial position t. We need to take care a little bit about the boundary conditions. So at the boundary, we have the following situation. We don't transmit the virtual positions. And the code bits of the virtual positions are not transmitted. They have erasure probability 0. So the variable nodes at the boundaries, they always have perfect knowledge. They are never erased. So CTL is equal to 0 if we add the virtual positions. These are the left virtual positions, and these are the right virtual positions. Okay, so now we can summarize. So density evolution looks like this. Everything is summarized over here. We first initialize CT0 is either 1, so we assume that everything is erased if we are in one of the useful positions, so one of the spatial positions that we actually transmit, so t going from 1 to L, or it's 0 otherwise. So that's the useful spatial positions and the initialization. And then we carry on the update. So for every spatial position that's useful, so from 1 to L, we carry out the update CTL, and we just use this update equation, and CTL depends on the 2w minus 1 neighboring spatial position. So we can go in one side t plus I minus j, or in the other side, depending if j is negative. So there is a window. CTL depends on a window around t, on the erasure positions around t. So there's kind of like a windowing or a filtering effect when you do this. It just looks like a filter. And then you carry out this, and if essentially all CTs are equal to 0, we can declare success, abort. And if we have a fixed point, so if all the CTs don't change anymore, it means we have reached a fixed point, and if this fixed point is larger than 0, we can declare failure and abort. And then otherwise, we just repeat this over and over again. So let's take a look at an example. So looking at an example, dv equals 3, dc equals 6, and epsilon equals 0.48. So we know that epsilon star of the 3.6 LDPC code is equal to 0.4292 roughly. So that's the threshold of the 3.6 LDPC code. And now we're looking at an epsilon of 0.48. So we are way beyond this threshold. With the 3.6 LDPC code, there is no hope that we can decode this. So let's take a look at what happens here. So this is after one iteration. This is L equals 1. We have the following situation. All the outgoing messages in the middle spatial positions, they are equal to 0.48. We have a total of 100 spatial positions. This is a typical example of what you're doing. And we have an erasure probability that looks like this. And we see that at the boundary, we have a slightly lower erasure probability. And this is because the check nodes at the boundaries, they are slightly smaller and they get information from the virtual nodes. So the virtual nodes, they inject their perfect knowledge. They said virtual positions are equal to 0. We don't transmit them. They inject this knowledge, and therefore the first spatial position has a slightly better erasure probability, and the last one has also a slightly better erasure probability. Very nice. So we look ahead, we look what's coming next. 2 iterations, then we have the following, and we see that the erasure probability in the middle decreases a bit, but also the ones at the boundary, they decrease even further. So already the first spatial position has erasure probability of less than 0.3. Continue further, 10 iterations, 20 iterations, 30 iterations, and we see that due to this filtering, we have this nice smoothing of the leftmost virtual positions. And we see that after 50 iterations, the first and the last spatial position is almost error-free or erasure-free. Almost all the erasures, they have been recovered. So this is actually pretty nice result and pretty nice example. And then after 100 iterations, almost the 2 first and the 2 last spatial positions have been recovered. And we see that this very smooth behavior now moves towards the middle. Let's see, 200 iterations. We have now 4 or 5 spatial positions that are recovered. And we can continue 300, after 500 iterations, we have recovered 15, 30 spatial positions almost completely, 0 erasure probability. So let's take a look. But after 1000 iterations, after 1200 iterations, there's just a small hump in the middle, and we can recover. And after 1400 iterations, we have recovered all the spatial positions. So we actually have a threshold that is at least 0.48 just by using the spatial coupling technique and having otherwise the same parameters of our code. This is just because of this small inconsistencies at the boundaries, and these boundary effects, they will push toward the code, through the code, toward the middle, and help recover everything that we have in our code. So can we go further? Can we go 0.49? Let's take a look. 0.49. After one iteration, the situation looks rather similar. 2 iterations, 10 iterations, 20 iterations, progress. But now we see that progress gets slower, slower, slower after 300, 500 iterations. So from 300 to 500, you can see here it changes, 300, 500. There is no change anymore, so we get stuck. We're in a fixed point. The threshold is not 0.49, but at least 0.48, so it's somewhere in between. If we spend more effort, we could find the threshold. We'll probably give it also on one of the next slides. So first we can define the decoding threshold. Again, it's the largest epsilon, such that all the CTLs converge to 0 if L goes to infinity. And this depends on the initialization that CT0 is equal to 1 if you are in the useful spatial positions, or 0 outside the useful spatial positions in the virtual. So yeah, this spatial coupling, this is something that dramatically improves the threshold. And the key to this is a slightly different check node degrees at the boundaries. And this is very similar to a nucleation effect that we have in physics. So you can see those super cooled water, for instance, and if you put some impurity in it, then it starts to freeze from this impurity, and it freezes slowly to the outside. And this is this effect we can observe in cooled water. There's also effect if sometimes you have this sodium acetate heating pads where there is a small metal piece inside. You put a metal, there is a liquid, and this liquid crystallizes and releases heat. And then you can return some energy by cooking it or boiling it. Then it returns to a liquid again. It stores this heat that it releases upon nucleation. There's a big similarity, some effects that we observe in physics. So the boundary effect is important because we can see that the check nodes at the boundaries, these check nodes, they have a lower degree. And the lower degree of a check node is usually good because that means that correcting the erasures is easier, simpler. You can recall check node is not erased, so 1 minus chi is equal to 1 minus then the input, the erasure input probability, so xc e to the power dc. So this is a number that is between 0 and 1. And if dc increases, this number gets smaller and smaller. So the probability that the check node is not erased, this is the probability that it is not erased, gets smaller and smaller if we increase dc. If the input messages is erased with the same probability. So if dc is small, the probability that the check node is not erased is going to be larger because of this expression. But actually good to have check nodes of low degree because then the probability of a message being not erased is larger, meaning the probability that the message is erased is actually going to be smaller. So the check nodes at the boundaries, they have smaller degrees, meaning they will be erased with smaller probabilities. The variable nodes at the boundary conditions, they will be erased with smaller probabilities, and therefore we have a better protection of the bits at the boundaries. So we have lower degree check nodes, they decrease the possibility of an erasure, and the check nodes at the boundaries, they have this lower degrees. So in the boundaries, they get decoded first, and then because of the spatial coupling, the effect propagates towards the middle. We start at the boundaries, they get decoded, and we propagate to the next one, they get decoded, and they propagate and propagate and propagate, and so on. So there's actually this propagation effect that helps us decode. So here we see some thresholds, and now the threshold depends on a lot of parameters. They depend on three different parameters, dV, dC, W, and L. We saw the case that we saw was 3, 6, W is equal to 3, L is equal to 100. We had a threshold of 0.48833 of the spatially coupled code. If we compare this to the uncoupled code, there's a threshold of 0.4292, 42944, sorry. But we get this threshold improvement by a small rate penalty. So instead of having a rate of 0.5, we now have a rate of 0.49. There is a small rate decrease, but we can see that the gain in threshold is much, much larger than the loss that we lose from the rate. And we see that the improvement of the threshold gets more and more dramatic if we increase dV and dC. And this is somehow counterintuitive because we knew that we have a LDPC code with increasing dV, the traditional threshold gets worse and worse and worse. But now the coupled threshold gets better actually. So for instance, for Bevel node degree 5, check node degree 10, W of 4, L equals 100, we have a threshold of the spatially coupled code which is 0.5 almost, compared to 0.34 with the uncoupled code. The rate loss will be larger because of a large W and because of a large DC, but by increasing L further, we saw that we can get rid of the rate loss. If we increase L much further, this will be the same threshold eventually. And we see that this is actually very, very close to the rate of the code. Thresholds, they are very, very close to the capacity limit. Capacity limit is 1 minus the rate, remember? Binary rate chamber, 1 minus the rate is capacity. And we can make this rate RDSC arbitrarily close to RD just by increasing L, because in the limit, both will be the same. So interestingly, this epsilon star decreases with increasing dV, which we have seen before, but epsilon star of the spatially coupled code actually increases. So this is a little bit unexpected because by spatial coupling, we increase, we have a completely different behavior than we have with the uncoupled code. Completely different behavior in terms of the threshold. And this was a little bit unexpected. And this drove people into looking at further into spatially coupled LDPC codes. And it was shown just 10 years ago now that what happens if this is the tail of the four limits. So if W goes to infinity and L goes to infinity in this order. So first L needs to go to infinity, then W needs to go to infinity. Then the rate of the spatially coupled code is just 1 minus dV over dC. And the threshold of epsilon SC is the same as the threshold if you would employ maximum likelihood decoding. So by using message passing decoding, we get exactly the same threshold as if we would use maximum likelihood decoding. And this is the same threshold as if you would use maximum likelihood decoding of the uncoupled LDPC codes. And this is why it's called threshold saturation, because the threshold saturates to the maximum possible, which is maximum likelihood decoding performance. So in the limit of L and W, the threshold saturates to the maximum likelihood performance of the spatially coupled LDPC code. And the maximum likelihood performance also in the limit of L and W is equal to the maximum likelihood performance of the uncoupled LDPC code. So that is a rather unexpected result, and it means that you can achieve the same performance as a maximum likelihood decoder could by using message passing, but you need to operate on a spatially coupled code. So what we can do then is we can take a code that has a good maximum likelihood performance, but where we don't know how to decode it. Then we apply spatial coupling with sufficiently large W at L, and with a message passing decoder, we can approach the maximum likelihood performance. This is very, very unexpected. So let's take a look at then what is the maximum likelihood decoding performance. This is something that we can actually calculate. We'll not prove this. This is a little bit beyond, even beyond what we are doing now, but we can actually calculate this for the binary erasure channel. So this ML decoding threshold of a regular SC-LDPC code can be described as. So we have this equation, this big equation, it's a polynomial equation, and we need to find the unique positive solution of this equation. That is called XML. So because of Descartes' theorem, we know that this has a unique positive solution. And we can just, for instance, numerically find this solution of this equation. And then we can calculate the maximum likelihood decoding threshold by just inserting XML into this equation. Proving this is pretty hard. It's by no means trivial. You need to take a lot of tricks to this. You need to have a lot of additional insights into the analysis of codes, and therefore we just give the final result. And you can actually prove that as dv goes to infinity, then the maximum likelihood decoding performance approaches dv over dc, which is 1 minus the rate, which is the capacity of the binary erasure channel. And this convergence is actually exponentially fast. We cannot prove this, but what we can do is we can plot this. So we'll plot it on the next slide, but we can summarize. We can use spatially coupled codes that are capacity achieving. If W goes to infinity, L goes to infinity, dv goes to infinity, n goes to infinity, and the number of iterations go to infinity. So if these 5 things go to infinity, or are very large, then we can construct a capacity achieving code. Otherwise, it's a little bit more difficult. But if these go to infinity, we can do this. And actually, even for finite variables, we can achieve very, 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 very good codes that outperform LDPC codes. So we have actually designed spatially coupled LDPC codes for some optical communication systems that have much better performance than conventional LDPC codes, also at very, very low power. So here we show the performance of the threshold. So we have DVDC regular LDPC codes. And we have the following. We plot the message passing threshold epsilon star. We saw this one is largest for dv equals 3. So here epsilon star is 0.42944. And we plot the maximum likelihood decoding threshold. And we see that the message passing threshold decreases very rapidly if we increase v, but the maximum likelihood decoding threshold approaches very, very fast the capacity of the binary erasure channel. Does it extremely fast. Great. So for more general channels, what can we do? Well, we can apply the Gaussian approximation. So the way it works is very similar than what we did before, so I'm just quickly going to summarize it. So for every spatial position t, we define the means of the Gaussian messages, so mu CTL and mu KTL. And we initialize mu CTL as being equal to mu C, the channel-related mean, the useful spatial positions, plus infinity or arbitrary or a very, very large number beyond the virtual positions. Then we can calculate the variable node outgoing message as mu CT plus dv minus 1 of sum of mu I t plus I. And we can do the check node. Now we can look at the check node message. Now it's a little bit more complicated because the incoming message is a sum of Gaussian PDFs. So we have essentially a Gaussian mixture that is going inside the check node. We can calculate, however, the mean of the check node outgoing message by looking at this, by using these expressions, and then we can finally formulate an overall update equation given by this guy. So this involved guy, essentially everything very similar to what we did before. All right, so we have looked at dense evolution and shown the outstanding performance of spatially coupled LDPC codes in terms of threshold. Now we're looking at a specific case, or a very interesting case, with one quite interesting result that we're going to see next video.